Hey everybody. So in this video, I'm going to introduce sugars. Now, this is really not a very long lecture. And the reason for that is that there's lots of kind of, I don't know if I want to say redundancy, um, but there's just, there's a good bit of information. Um, but anyway, we'll get started on it. Okay, so sugars. Now, first and foremost is you will hear a couple of different terms to identify sugars. One of those terms that you'll hear is saccharides. And what you'll hear is you'll hear monosaccharides. You'll also hear polysaccharides. And these are two terms that are regularly used for sugars. A monosaccharide is a monomer. So it is a single sugar molecule. A polysaccharide is multiple, and I'll say it's typically going to be three plus. And then one last term that we'll hear from time to time, and we'll talk about in this class, disaccharide, which is just going to be two sugars. Okay. Now, sugars are molecules that are made up of basically I would say 90 plus percent of them, of all the different sugars, 90 plus percent of them are nothing but carbon, hydrogen, and oxygen. Now, there are some sugars that are going to have something else. For instance, if you've ever heard of the artificial sweetener sucralose, sucralose actually has chlorine as one of the elements within it. But that would be kind of an exception to the rule as opposed to, the letter of the law. So when we talk about monosaccharides having pretty much nothing but carbon, hydrogen, and oxygen, we have what's known as a empirical formula. An empirical formula, or basically kind of a basic ratio that is C sub X and then H2O sub X. What that means is that that X can be any number of different numbers. So, for example, if you make a monosaccharide with four carbons, you would have a formula of C sub 4. Then you take this H2O right here and you'd multiply the 2 and the one that's not there for the oxygen times 4. So you'd have C4H8O4. So that would be a four carbon molecule. That would be, and this is where we're introducing some more terminology. This would be a tetrose. That suffix OSE is indicating that you're talking about a sugar. And let me go ahead and erase poly here because I don't want any confusion. So whenever you see a suffix of OSE, I want you to think, okay, that's talking about a sugar. Okay. Now here are some examples of very common sugars. For example, glucose. That's maybe the most common sugar that you've ever heard of or that you have encountered. Glucose is also sometimes called dextrose. Dextrose has six carbons, so that X right here would be a six. Then you would see that six over here, but we'd apply that to everything in the parentheses, which is how we would arrive at 2 times 6 or 12, and then 6 times the 1 for the oxygen, that would be 6 as well. So C6H12O6 is the structure, is the formula for the molecule glucose. Glucose is an example of a hexose. So we've actually got quite a few different names for one molecule. Glucose, formula C6H12O6, is also known as dextrose. These would be kind of the, like, I would say more common, like industrial names that you would hear. Glucose slash dextrose is an example of a hexose. Okay, now let's talk about that name hexose. Hex indicating six, OSE indicating that it's a sugar. Hexose, that is a sugar that has six carbons. So looking at this list down here, from fructose to glyceraldehyde, do you see any other hexoses? Yeah, fructose is a hexose because it also has that formula of C6H12O6. Galactose is also a hexose with a formula of C6H12O6. So we have these molecules that, there's three of them right here that have the exact same formula. Now we'll look at how they differ from one another, but these are examples of isomers. Now, we previously talked about cis and trans isomers, basically compounds with the exact same atoms but positioned in different ways. We've got the same sort of thing, but it's not about, or it's not a repositioning of one single group relative to a double bond. Instead, we've got these three different molecules that we're working with. Okay, so if we look at our other sugars that are listed down here, so we've got glucose, fructose, and galactose, which are all hexoses. Then we've got ribose. How do we classify ribose? Well, it's got five carbons, so that would be an example of a pentose. It has five carbons, that OSE suffix, so pentose. Our last one has a little bit of a different name, glyceraldehyde. This is three carbons, so C3H6O3. And this would be an example of a triose. Okay, so our molecules, they can vary quite a bit. And this list over here on the right-hand side shows basically our number of carbons ranges from 3 to 8. And that's pretty accurate for the most common. That's a good test question. Most common number of carbons in a sugar. It's pretty uncommon to find a sugar that's 9 carbons or 10 carbons. You would follow it's possible, in which case you would have this different prefix. If it was 9 carbons, it would be nanos. If it was 10 carbons, it would be decos. But like I said, the frequency, how commonly you see those, it's not very often. So that's why we stick with 3 to 8 as the range for our sugars. Now, our other two sugars, or sorry, these last two terms at the bottom, aldehydes and ketones. Okay, remember when we talked about organic functional groups? We talked about aldehydes and we talked about ketones. These terms are very important because that's actually how we classify sugars. Sugars can be, and oh, I want to bring these two words up, or we'll start with one of them, that OSE, oses. I mean, there's an extra S at the end to indicate multiple or plurality, but ose, that indicates a sugar. An aldose is a sugar with an aldehyde functional group. And then we've got oses again with ketoses. So a ketose is a sugar with a ketone functional group. So this slide right here, there's a lot to unpack. We've got some examples of specific sugar names. If you're to walk away with anything from this, I would walk away with a couple of things. One, that overall formula or that empirical formula the ratio of our carbons, hydrogens, and oxygens to one another. This right here. Be able to do the calculation where if I said, okay, well, we found a sugar that has 62 carbons. Well, what would it be? What would the formula for that be? It would be C62, H124, O62. Okay, so be able to manipulate that. Next up, know the difference between a monosaccharide, a disaccharide, and a polysaccharide. Okay. Then after that, know this range, know these prefixes from tri to oct. So from 3 carbons to 8 carbons. Then last but not least, what's the difference between an aldose and a ketose? What does an aldehyde functional group look like, and what does a ketone functional group look like? Now, a little bit of a, not necessarily a spoiler, but all of the sugars that we're going to look at are either going to be aldoses or ketoses. So here are examples of our different sizes. We've got a 3 carbon, and this actually shows our most frequent. If you remember over here, I said most common, basically 3 to 8 carbons. I would classify that even, like narrow that down a little bit more, whittle it down a little bit more. And we're actually not going to look at any 7 or 8 carbon molecules. We'll look at all of the sugars from 3 carbons to 6 carbons. That means we will look at our trioses, tetroses, pentoses, and hexoses. Now, one of the things that I want you to look at is we have carbons at number 1, 2, and 3. Now, if you look at carbon number 2 in glyceraldehyde, we have a hydroxide group or an alcohol group on the right side of the molecule. Now, that's really important. If that OH group is on the right-hand side or the left-hand side of the molecule, that's going to give you a different sugar. For example, our tetrose has a common name of D-threose. Now, any of these names that are highlighted in green, I'm not expecting you to know those structures. In a few slides, I'll show you basically 5 aldoses and then 3 ketoses that I want you to know those structures, but that's the extent of the structures that I want you to know. But my point whenever I say D-threose, if this hydroxide group was on the right-hand side of the molecule, so if it was right here, that would not be D-threose. Okay, so the positioning of different groups is significant for the name. So as we see this, this is D-threose. Next up, D-ribose is a pentose, and then D-glucose, our old friend, aka dextrose, is an example of a hexose. Now, to bring back the terminology of an aldose or a ketose, on the left-hand side, we have D-glucose. This is an example of an aldose. We have that aldehyde functional group at carbon number 1, 2, 3, 4, 5, and 6. Then our molecule on the right-hand side. That's a ketose. Okay, so essentially, what I want you to look at when you look at a aldose versus a ketose is you have a double bonded carbon, a carbonyl carbon. Is that going to be at carbon position 1 or is it at carbon position number 2? So what we have to draw this a little bit more explicitly, here is D-fructose. This is going to be H, OH, C, OH, OH, H, CH2OH. Okay, so this carbonyl carbon, and then I'm going to draw this a little bit differently. Here's our, well, I can redraw that. and 6 CH2OH, OH, OH, H, H, OH, H, H. Okay. So this is an aldose on the left-hand side and a ketose on the right-hand side. This is an aldehyde functional group versus a ketone functional group. They both have a carbonyl carbon, but the question is, where is that carbonyl carbon? Is that carbonyl between two carbons, or is that carbonyl only have one carbon on the side of it? And whenever I say only on one side, I'm referencing like this carbonyl carbon obviously has a double bonded oxygen, and then it has a hydrogen that it's bound to, and this chain of carbons. This carbonyl carbon right here, well, it has a CH2OH and then this chain of carbons that it's bound to. Now, when it comes to aldoses, I'm showing you this because what I want to do is I want to illustrate the differences between sugars. Now, in terms of sugars that are important for you to know, and all that you'll need to do is be able to identify them, is I want you to be able to identify glyceraldehyde, ribose, glucose, mannose, and galactose. Okay, these are ones that I will give you test questions over. Now, the reason that I'm going to give you test questions where I ask you, what is this sugar, is because these are the most, to put it no other way, they're the most physiologically relevant or biologically relevant sugars. Now, these are all aldoses. One time, or sometimes, I'm going to redraw deglyceraldehyde or glyceraldehyde here. It looks like this. Sometimes you'll take that CHO, or what people will do is draw CHO, and what they really mean is this right here, C, and then that aldehyde functional group. So that's something that takes you a minute to kind of wrap your mind around, but that's essentially what we're looking at there. Now, if you look at D-ribose here, or ribose, and this does have an additional designation of a D sugar. I'm not going to go into that. But that's a property of these sugars, and basically how they respond to light. So if you look at arabinose and ribose, let's start at carbon number 1 for both of these. They both show up as CHO. Now let's go on to carbon number 2. Okay. In ribose, we have HCOH. Compared to arabinose, you have HOCH. Those are different. What that's depicting is that arabinose has the hydroxide group or the OH group on the left-hand side of the structure that ribose has on the right-hand side of the structure. So these two sugars, ribose and arabinose, the difference between them is their positioning of an OH group on carbon number 2. But before we draw that complete conclusion, let's see if there's any other difference. Carbon 3, carbon 4. They both, or sorry, carbon 3 for both of them. I'm going to cross these both out so we can kind of focus in. Well, they both show up as HCOH. Okay, those are the same. Then carbon 4, HCOH. Okay, those are the same. And then the last carbon, CH2OH, those are the same. So when you compare ribose and arabinose, the only difference between them is the positioning of the OH group on carbon number 2. So that's where I bring that up, because that means that these two sugars are different. And the significance of that is not just like, oh, well, I draw them differently. Instead, your body can detect the difference. Your enzymes, the agents of like extracting energy from these compounds, they can detect a difference. So, for example, if you got a Dr. Pepper that was sweetened with, let's say, glucose compared to mannose, these two sugars, the only difference between those sugars is the positioning of the OH group on carbon number two. And your body is going to be able to detect the difference because your body is going to have to process mannose in a different way than it would process glucose. Now, again, like I said, the sugars that I want you to know the structures of and be able to recall the structures are the ones that are boxed: glyceraldehyde, ribose, glucose, mannose, galactose. Now, all of these sugars are aldoses. You have an aldotriose. That term right there, aldotriose, tells you that you have an aldehyde functional group, tri meaning three, and then OSE meaning it's a sugar. So it's an aldotriose. Then you've got your aldopentoses. It's an aldehyde functional group, five carbons, and that OSE, it's a sugar. So this is a five carbon sugar with an aldehyde functional group. Then last but not least, we've got aldohexoses, aldehyde functional group, and it's a six carbon sugar. All right. So now we can move on to our ketoses. So our ketoses, there's fewer of them. There's three ketoses that I want you to be able to identify the structures of. They are dihydroxyacetone, ribulose, and fructose. Okay, so the differences between dihydroxyacetone, ribulose, and fructose. Well, this is a keto triose. Erythrulose is a keto tetrose. Ribulose is a keto pentose. And then fructose is a keto hexose. Now, just as a little bit of an aside, I remember I was talking in a class a few years ago about ketoses, and I had a student who raised their hand and they asked, well, are these ketoses, are these sugars that are good for the when you go into ketosis, are they good for the keto diet? And I had to let them know that no, they're not. Fructose, for example, is a sweetener in most foods that you eat. If you've ever heard of high fructose corn syrup, chances are that's the artificial, or not the artificial, but that's the sweetener that's in your food. It's the sweetener that's in most sodas and, well, most things. And that causes your blood sugar to go way up, and it is a sugar. Ketose, that keto has to do with that functional group, that ketone functional group. So we've got our keto triose, dihydroxyacetone, our keto pentose, ribulose, and our keto hexose, fructose. The most important thing about this is understanding where that carbonyl group is. It's I apologize. It's on carbon number two. Carbon three, four, five, and then three, four, five, six for our fructose. Um, Again, these are just molecules that I'll show you the structure of, and I'll ask you, what is this? Okay. Now, despite aldoses and ketoses having this what's known as a linear form, what they really love to do is they love to form rings. They love to cyclize. Now, these are what are known as Haworth structures. I'm not going to ask you about what a Haworth structure is, but what this shows is if you notice that this line right here, I'm going to circle the line. Well, it's not really a circle, but I'll draw around this line. Notice how it's bolded. That gives you an indication of approximately where it is in 3D space. That's telling you that that line's coming toward us. Okay, so the idea is we're drawing a molecule in two dimensions, so on our X and Y plane, but we have some depth for that molecule. We can look at it and make some kind of conclusions about where different groups are. Now, this is glucopyranose. This is also glucopyranose. This is alpha glucopyranose. This is beta glucopyranose. And the difference between these, well, just like any other sugar, has to do with the positioning of OH groups. Now, the the difference between these two sugars, whenever you look at them, let's go ahead and just pick this CH2OH. Okay, I'm going to say that this group is pointed up with respect to my ring. So it's like it's pointing above my ring. It's pointed in the north direction. Then if I find this OH group, it's pointed down. This OH group is pointed up. This is down. And then this last one is also pointed down. Okay. Now, what I want to do is I want to identify which carbon or which OH group gives me the designation alpha as opposed to beta. Now, since this is a ose and it's gluco, this pyran has to do with that's a specific name for this ring, this six-membered ring. So this is glucose. That's glucose. Cyclized or ring-formed glucose is also known as glucopyranose. So just kind of commit that name to memory. Glucopyranose means glucose as a ring, basically. Now, let's look at our beta glucopyranose. Well, this carbon right here is pointed up, just the same as this one over here. Okay, this OH group is pointed down. Well, that's the same as this one. This OH group is pointed up, much like this one is. Okay, so these are both pointed upward. Then this OH group is pointed down, the exact same as this one. Okay, so we have no difference so far. We've been working counterclockwise, looking at our different groups around the ring. And last but not least is this OH group. Okay, that one's pointing up. Okay, so I'm going to basically erase everything and leave behind only the groups that are different from one another. The only groups that are different from one another is this OH group and this OH group. The OH group on my molecule on the right is pointed up, whereas the OH group for the molecule on my left is pointed down. Okay. I want you to keep that in mind. If that OH group, if the different, I'll say if the different OH is down, then it is an alpha sugar. If the different, I'm going to say different OH is up, then it is a beta sugar. So we have two different sugars, an alpha and a beta sugar, and the positioning of that OH group. So when you compare two different or two sugars like this is actually carbon number one right here. This is carbon number one right here. So the positioning of so this is one of the things that I might ask you to do is I'll give you a sugar and I'll say, here are two sugars that are identical, but one of them's the alpha and one of them's the beta. Pick which one is the alpha, pick which one is the beta. That's a test question that I want you to be able to answer. And you'd be able to say, okay, well, my different OH group, since I know that the two sugars are otherwise identical, they're both glucose, they're both fructose, they're both mannose, whatever. I see this carbon is different, or this OH group is different. It's pointed down, therefore, this is an alpha sugar. So these sugars are commonly known. So when we talk about an alpha and beta sugar, these are what are known as anomers. These are molecules that they only differ about that one carbon. All right. So when we talk about anomers, much like these two, oh yeah, sorry, I wrote the word anomers, but then I have writing all over it. So anomers, there we go. When we talk about anomers, that's really kind of our primer to begin a conversation about disaccharides. Now, there are three major disaccharides that I want you to know: sucrose, lactose, and maltose. And the reason is that these are very abundant. Sucrose is a sweetener in lots of candy and other foods that you may eat. Now, disaccharides are sugars that are made up of two rings. Okay, so sucrose as a disaccharide has these two rings. Now, sucrose is a disaccharide made up of glucose and fructose. It's two rings that have basically reacted with one another to make a linked molecule. Now, the linkage between them is known as a glycosidic linkage. Okay. What I want you to take away from this is not that it's a glycosidic linkage. I want you to know that sucrose is a disaccharide of glucose and fructose. Look at that. It looks like a heart, but it also kind of looks like a face. Yeah. Anyway, um, sucrose is a disaccharide of glucose and fructose. Now, sucrose, the way that it can also be depicted is like this, where we have this ring is this ring. This ring is this ring. And there's our glucose and fructose. Our other two disaccharides, lactose and maltose. Lactose is a disaccharide made up of galactose and glucose. Maltose is a disaccharide made up of, now let's take a minute and look at this. First of all, let's look at this molecule right here. This is carbon 1, this is carbon 1. Our OH group is pointing down. That means that this right here is an alpha sugar. Let's look at our other carbon number 1. Well, it's no longer an OH group, but that oxygen is pointing down, meaning this is also an alpha carbon or an alpha sugar. Now, this is maltose, which is a disaccharide of two glucose molecules. So, and they're connected through, again, a glycosidic linkage. Now, the numbering here that's shown is alpha 1,4 glycosidic linkage. That's between carbon number 1 and carbon number 4, where the bond is formed. Now, again, what I want you to know about this is I want you to know that lactose is made up of glucose and galactose. Maltose is made up of glucose and glucose. Sucrose is glucose and fructose. Lactose is galactose and glucose. Maltose is glucose and glucose. Now, are these the only three disaccharides? No. There's tons of different disaccharides, and there's a lot more to those disaccharides. In terms of disaccharides that you'll encounter on a somewhat regular basis, these are the three big ones. You know, if you go and drink milk or something like that, if you go to HEB and you get Mutopia brand sugar, or sorry, Mutopia branded milk, well, that is milk in which lactose has largely been taken out of it because people don't want the extra sugar. Maltose is glucose and glucose, and that's pretty regularly found in a number of different industrial processes. And if I remember correctly, it's also involved in the beer making process. Um, so these are the three disaccharides that I want you to know. I want you to know what they're made up of, the sugars that they're made up of, and I don't expect you to be able to draw them or identify their structures, but I do want you to know the players that are involved in making them. Like I said, this was a fairly short but kind of dense lecture. Um, if you have any questions about this, please don't hesitate to contact me. Um, I'm going to probably set up some office hours on Friday so that if you want to talk about any of this, if you want to go through some example test questions where that could come from this, I'd love to talk to you. Other than that, though, I hope you have a great day and I'll see you later.